14th online lecture session of the course Engineering Thermodynamics. In our previous lecture, we have concluded our discussion on first law of thermodynamics for closed system. Okay, so in this particular lecture, we will have a detailed discussion on the first law of thermodynamics, and in particular, we will be actually trying to analyze open systems from the energy conservation point of view. Okay. So let me just write the topic. So our today's topic is nothing but first law of thermodynamics, and this we are studying for open systems. Okay, or I can also write control volume systems. Okay, so for open systems, we have to study the first law of thermodynamics. So one additional thing will be happening. So we already know that for a closed system, del Q minus del W equal to delta E. So this much we know from the conservation of energy principle that we call as our first law of thermodynamics for closed system also. Now what will be happening in case of open system, because across the boundary of the system we will be having some mass flow also. Okay, so for example, you can consider this as our control volume. So now if I consider this as control volume, you can clearly see that from the left I have certain input for mass flow. So mi, I am writing now mi dot. So the meaning of mi dot is dmi by dt. Here mi is mass at the inlet and dt represents the rate of change of mass at the inlet with time. Okay, so that's why this m I am writing as m dot, because now what we are having this mass in flow. So certain amount of fluid will be actually flowing through the inlet. So if it is flowing through the inlet, so obviously it will be in the rate form. Okay, so that's why. All of you, please keep your microphone muted. Okay, so what we are having, we have some inlet, and from that inlet we are having the flow of certain amount of mass. So that's why we are writing mi dot. Okay, similarly we will be having certain flow which will be actually moving out of the system, so that we will be calling as nothing but our m dot o. Okay, so I am referring to inlet and o I am referring to outlet. So it means that if we are having certain amount of flow from the inlet, so obviously a certain amount of flow is there from the outlet. So it means this mass will be carrying certain amount of energy also, because we already know that it is the inherent nature of the mass that while we are having certain amount of mass, with that certain amount of energy will be always associated. Okay, so that's why while this mass will be coming through this boundary, okay, it is actually getting into the system, it will carry certain amount of energy also. So let me write that energy as nothing but ei, and while this mass is leaving out of the system, once again it will carry certain amount of energy. So I am writing this energy as nothing but EO. Okay, so EI and EO are nothing but the amount of energy which are associated with the mass which is coming at the inlet and going at outlet respectively. Okay, so what we have to do before just going into the energy analysis, let us first try to see the conservation of mass, because we have certain inflow of mass and certain outflow of mass. So obviously for this control volume we have to also define the conservation of mass. Okay, so in order to study the conservation of mass, what I will be doing, let me take some more generalized system. So what I am doing, I have taken a turbine. So turbine is nothing but a device in which actually we allow on the turbine we allow liquid to flow over it. Okay, and it has certain shaft and certain impellers, So while the liquid will be flowing over it, these impellers or rotors of the turbine are connected to a shaft. So while our fluid will be flowing over the turbine, so from here we will allow certain high pressure fluid to enter over this turbine. So while this fluid will be flowing over the turbine, what will be happening? Its shaft will be rotating and we will be getting certain amount of work which we call as nothing but shaft work. Okay. Now this rotation will continuously varying with time. So that's why whatever the work we will be getting from the turbine, that we will be calling as W dot S. So here W dot S is nothing but equal to dWs divided by dt. So Ws is our shaft work. Now because shaft is continuously rotating with time, so obviously work will be a function of time. So rate of work done we are calling as W dot S. So let me say that W dot S is the amount of work done, a rate at which we are getting work done from this turbine. Okay. Now what we are doing, whatever the steam is coming from this turbine, say at the outlet of the turbine, we are getting certain amount of fluid. So turbine can be of any type. It may be steam turbine, gas turbine. Okay, so if we are allowing high pressure gases to expand, then it will be gas turbine. If high pressure steam is expanding, then it will be steam turbine. So we will try to see the energy analysis of turbine also in our next lecture. Just for this particular case, only remember that turbine is a device which will be converting the energy of the fluid into mechanical energy in the form of shaft work. Okay, so this high pressure inlet will be coming, high pressure fluid will be coming at the inlet of the turbine, and from this turbine, say we are this steam is actually going out. Okay, now what I am saying that while this steam is going out, part of the steam I have passed through certain device, and that device is nothing but an accumulator. So this we are calling as nothing but an accumulator. So accumulator is it will be having certain volume, and inside that volume actually certain amount of fluid can be stored. Okay. Then let me once again take that whatever the remaining amount of steam. So for example, if total amount whatever was coming, I have not taken entirely, I have given some fraction of steam to this accumulator. Okay, then whatever the remaining amount was there, that further remaining amount I have passed through once again piston cylinder arrangement. Okay, so now let me see, I have a cylinder and over here I have one piston. Okay, and few amount of steam I have also passed through this piston cylinder arrangement. So obviously while this piston will be displacing, it will be doing certain amount of displacement work. So let me call that displacement work as nothing but say WD. Okay. So what we are doing basically, initially we have passed high pressure steam over turbine, then whatever the steam at the outlet of the turbine we were having, some amount of steam we have passed through one accumulator, some amount of steam we are passing through one piston cylinder device, and say some amount, and whatever the remaining amount of steam we are having, let's say this we have actually sent outside. Okay. Now, if I consider that this particular boundary, whatever I am drawing with the dashed line, this is nothing but my control volume. All of you, please keep your microphones muted. What I am saying now, this is my, this particular boundary is nothing but my control volume. Okay, so this is my control volume which I want to study, or this is, I can say that this is nothing but my open system. Okay, why I am calling this as open system? Because while I have defined the boundary, you can see that at this particular point certain mass is actually entering. So I'll be calling, say, mass is entering at m dot I rate. Okay, and at this particular point what we are having certain amount of mass which is going out of the boundary of the control volume. But if you see inside this control volume, we have certain arrangements. For example, this is an accumulator. So accumulator is nothing but it's like a tank-like device where some fraction of the steam or whatever the working fluid we are having, that will be actually stored over here. Okay, then we have this piston cylinder arrangement. So while this piston will be expanding, once again it will store certain amount of steam inside this, certain amount of working fluid inside this cylinder. Similarly, certain amount of working fluid, if initially say this we are starting from the first instant, then obviously certain amount of fluid will be accumulated inside the boundary of the turbine also. So that's why what will be happening, because we are having within our control volume certain devices where some fraction of the working fluid can be stored. So that's why what will be happening, whatever the rate we will be having at the inlet inflow, same amount of rate will not be at the outlet. So that's why what I will be saying, that say m dot E is nothing but the rate at which our working fluid is coming out of the control volume. Okay. So now if I have to define the conservation of mass for this control volume, based on the conservation of mass, I can write that whatever the mass inlet we are having minus whatever the mass flow out we are having. So that's why I am writing everywhere dot, because we are talking in terms of rate. So that's why what I am saying now, mass inlet minus mass outlet will be nothing but the rate of change of mass of the control volume. Okay, because what I am saying, that inside this control volume we are having certain devices which can actually store certain amount of mass of the fluid. So that's why the mass of the control volume will be changing, and the rate at which mass of the control volume will be changing, that will be nothing but inflow mass minus outflow mass. Okay, so for this particular system, because I am writing inflow and outflow as mi dot and me dot, so I can simply say that my mi dot minus m dot E is nothing but equal to dmCV divided by dt, where mCV refers to as the mass of the control volume, and m dot I am calling as nothing but dmi by dt. Similarly, m dot E dme divided by dt. Okay, so this is nothing but mass flow rate at the inlet and mass flow rate at the outlet. So in this particular control volume, we have seen that we are only having one inlet and one outlet. So that's why we are writing that inlet minus outlet mass flow rate is nothing but equal to rate at which mass of the control volume will be changing. Okay, so you can clearly see, if our mi dot is more in comparison to me dot, in that case we will be having dmCV by dt as positive, and mass will be accumulating inside our control volume with time. Okay, with increase of time. If our mi dot minus me dot is negative, it means the mass which is going out, that is more in comparison to the mass which is coming in. In that case, we will be having actually decrease of mass of the control volume with increase of time. Okay. So now this particular example, whatever I have shown you over here, this is related to the single inlet outlet system. Now in our control volume, say if I take any generalized control volume, so in our control volume, we may have multiple inlets. So for example, M1 dot, M2 dot, say M3 dot, I may have multiple inlets. Similarly, I may have multiple outlets. For example, M4 dot and M5 dot I am taking as my outlet. So in that case, what will be happening? That M1 dot plus M2 dot plus M3 dot. This is the total mass which is entering inside, minus we are having M4 dot plus M5 dot as the mass which is going out. That will be nothing but equal to dmCV divided by dt. And in general, if I have to specify, so I can write that summation of all the inlet masses. Okay, so m dot I over here refers to inlet. So summation of all the inlet mass minus sum of all the masses which are going out of the system So there also I'll be writing actually dot mass flow rates. So mi dot summation minus me dot summation is nothing but equal to d into m d into m control volume divided by dt. So this is in general statement for a control volume when we are defining the conservation of mass. Okay. Now, after the conservation of mass, it is important to define another important principle, that is nothing but conservation of energy. Okay, so now we have to see the conservation of energy. So in terms of conservation of energy, once again I will try to draw a system, control volume almost identical to that what I have shown you earlier. Once again I am showing that we are having a turbine. Okay, and then we have, say, certain arrangement over here where working fluid is actually being stored in this particular arrangement. Then from this we have certain outlet also over here, and somewhere over here we have one piston cylinder device also. Okay, so I am drawing one more control volume. So this particular control volume we will utilize to define our nothing but conservation of energy. Okay, so now once again what I have taken that certain amount of inflow is there at the rate of mi dot to the turbine. Then from the outlet of the turbine it is going inside some chamber, and from this chamber then certain amount is actually entering inside the piston cylinder. So certain amount of fluid is entering inside the piston cylinder, and a certain amount of fluid is actually going out of this chamber, and let us consider that me e dot is the rate at which mass is going outside. Okay, and what we will be now considering, we have to now define the boundary. Okay, so let me now define the boundary for this control volume. So let me consider that this is my boundary of the control volume. Okay, so this is my boundary of the control volume. Now let me also write over here, we will be getting certain amount of shaft work at the rate of w dot s. Here we will be getting certain amount of displacement work at the rate of w dot d. And what else I am saying? I am saying that in this particular case, say we are also adding certain amount of heat to the fluid inside this chamber, whatever I have taken. So I am writing rate of heat transfer as nothing but q dot. Okay, so once again the meaning of q dot is nothing but equal to dq divided by dt. Okay, so the rate at which heat is being added that we are defining as q dot, which is nothing but equal to dq by dt. So now already we know that for closed system our del q minus del w equal to delta E, or in general form, if you want to write in the rate form, so you can write del Q by dt minus del W by dt is nothing but equal to dE divided by dt. So that is in the rate form, we already know. But what about the control volume? So now, as I have already told you, while we will be having certain inflow of the mass through the boundary and a certain outflow of the mass across the boundary, in that case what will be happening, that inflow and outflow mass will also carry certain amount of energy. Okay, so the amount of energy which is carried by inflow mass I am calling as that as nothing but my EI, and specific energy which is taken out of this control volume, that I am calling as nothing but my EO. Okay, so while this MI mass is entering into the control volume, actually it is carrying EI amount of energy, and while it is leaving, it is carrying EO amount of energy. Okay, so now if I have to now define the energy equation, I am adding heat transfer at q dot rate. So I'll be writing q dot minus, in terms of W, if I see, So both the works are nothing but done by the system, because piston is also moving out and this turbine is also rotating because of the fluid pressure. So both these works are actually done by the system. So work done by the system is taken as positive. So I'll be writing over here W dot S plus W dot D. This is my total work done, whatever we are actually, our system or our control volume is doing. Apart from that, earlier what we used to do, we used to write only the transfer of energy across the boundary of the system, either in the form of heat or in the form of work, okay, or both also sometimes takes place simultaneously. But when we are talking about the control volume, now we have to consider heat transfer, work transfer, plus we have to also include the energy carried by inflow and outflow of mass. So that's why what will be happening, we are having mi dot as the mass which is entering inside the system. So I have to write over here mi dot into I multiplied by EI is the energy which it is carrying. So this is the energy which is entering into the control volume, because Mi mass is actually entering inside the control volume. Now we will be having a certain mass which is going out. So mass which is going out is nothing but Me dot, and the corresponding energy is EE. Okay, so here this E refers to specific energy and small e subscript refers to exit which is going out of the system. So instead of EE, I can also use symbol MO for outlet. So let me use symbol EO so that it is not confusing. So over here also I have written, I think, MO and EO. So let me use, for outlet I am using symbol, say, subscript O. Okay. So this is the energy which is going out, because this mass is going out. Okay. So this will be nothing but equal to change in energy of the control volume. So I'll be writing change in energy of the control volume as dECV divided by dt. So if ECV I am defining as nothing but energy of the control volume. Okay. Now in this particular equation, what is EI? EI is nothing but our internal energy of the inlet stream plus kinetic energy, because now we are having flow. Okay, fluid is flowing with certain amount of velocity. So that's why we will be having kinetic energy also. Okay, so let me write kinetic energy as half into V bar square. So what I am doing for velocity, I am using symbol V bar. So V bar symbol I am specifying for velocity. So this V bar I will be considering at the inlet. So V bar I square plus, say, if Z1 is the elevation of inlet, so I'll be writing over here nothing but GZI. Okay, so ZI is the elevation of the inlet. So this is the total energy EI, and this nothing but comprises of internal energy, kinetic energy, and potential energy. Similarly, if I have to write down EO, from our understanding, it will be nothing but equal to UO plus half V bar O square plus GZO. Okay. Now, this formulation of energy, whatever we have written, whatever the knowledge you are having at present, it may appear to you that this particular formulation is correct. Okay. However, I want to just tell you that over here in both these energies EI and EO, we are having one more term which is actually pending. Okay, so we have to add one more energy over here. So I am putting this plus sign over here, and after this plus sign, now let me explain that what energy we have to now include over here. Okay, so the energy which we have to include over here, that particular energy is actually known as flow work. Okay, so the energy which we have to include in our inlet stream and outlet stream now, because I have put one more plus sign, so we have to include something over here. So the quantity which I have to add over here, that particular quantity is something which we call as nothing but our flow work. Okay, so now how that flow work will be coming into picture. Let me first explain the idea of flow work. Then I'll be once again going back to the previous slide in order to complete our conservation of energy. Okay. So the idea is, while we are having a pipe, say a fluid is flowing inside a pipe. So what I am saying, a fluid is actually flowing inside a pipe. Now, one important thing we already know, that while the fluid will be flowing inside a pipe, fluid always flows from high pressure to low pressure. That is something which we know. So we will be having high pressure over here and we will be having low pressure at the outlet. Then only we will be having flow of fluid in this particular direction. Okay. Now, if whatever the fluid we are having at any instant in the pipe, if I divide that fluid into multiple parcels of fluid. So what I am saying, I am dividing this entire volume of the fluid into small elemental volumes. Okay, and these elemental volumes I am calling as nothing but the different parcels of fluid. Sorry. So this is what I am saying over here, that I have fluid nothing but in the form of multiple parcels of fluid. So one important thing you can see over here, if this particular element of the fluid has to move in rightward direction, obviously this element will be getting certain push from the element which is just behind. Okay, so similarly you can say that whatever the successive element we are having, that is getting the push from the its preceding element. Okay, so from the preceding element of the fluid. So that's why while fluid will be flowing, certain amount of work is actually done by the fluid elements, the different layers of the fluid, in order to make the flow through the pipe. Okay. So in more details, let us try to understand this concept and let us try to quantify also with the help of one more illustration. So in another illustration, what I want to take, say I have a pipe, and in this pipe over here I have certain valve fitted, and now say inside this particular pipe the flow of water is happening, and say water is flowing at temperature of say 25 degrees Celsius and pressure of 600 kilopascal. So it means inside this main pipe, whatever the fluid pressure we are having, that is nothing but equal to 600 kilopascals. Okay. Now what I want to do, I want to add, say I want to now add certain amount of mass of water. So MW, mass of water, I want to add. Say it may be say something around 10 kg or 15 kg more water I want to add into this pipe. Okay. So like easiest option you can think of, that you will be opening this valve. You will be opening this valve. Now take a bucket and with the help of a bucket, try to put 10 kg of water inside. You may think of that thing. Okay, so say this, we are having some arrangement over here in order to access the pipe fluid. So that's why you just think of that, okay, open this particular valve. Now take a bucket which is having 10 kg of water, and from that bucket just pour the water into the pipe. Will it be possible? So we are having inside pressure of the pipe as nothing but 600 kilopascal, and outside pressure is atmospheric. So outside pressure is 101.325 kilopascals. Okay. So now if I open this valve and if I try to pour the water with the help of bucket, I will not be able to do it, because while I will be opening the valve, because inside flowing stream pressure is actually more in comparison to the pressure of the surrounding. So that's why it will be the inside fluid which will be flooding out of the pipe rather than the bucket fluid which we are trying to pour inside. Okay. So it means we will not be able to pour by using this method. So now what I can do, I can devise one more arrangement. I can devise one more arrangement where at the other end of this wall, I will be actually connecting nothing but a piston cylinder arrangement. Okay. Now what I will be doing inside this piston cylinder arrangement, I will be actually taking, say, whatever the amount of water I want to pour. For example, if I want to put inside 10 kg of water, so I will be taking 10 kg of water inside this piston cylinder, and then I will be applying certain amount of force over here. So certain amount of force I'll be applying over here, and this force will actually try to increase the pressure over here. And once pressure has become sufficient in order to pour the this liquid, whatever we have taken inside, into the pipe, then obviously it will be flowing inside the pipe. Okay, so nothing but we are using some mechanical arrangement and we are subjecting certain amount of force to this particular mechanical arrangement. Okay, so now what we have to do, if you carefully see, we know that work is nothing but equal to force into displacement. So if I write del W, that will be nothing but equal to F into ds. Okay, now we know that here we have to do the work with the change of time. So rate of work done with reference to time will be equal to nothing but F into ds by dt. Okay, so what is ds by dt? ds by dt will nothing but give you your velocity. So I can simply say that whatever the work which we are doing over here in order to fill this 10 kg of liquid, or whatever, say m kg of mass of liquid into the pipeline, that work has to be done at the rate of F into V bar, because I am saying that ds by dt is nothing but S refers to displacement. So rate of change of displacement with time will be nothing but our velocity, and for velocity I am using symbol V bar. Okay, now if I say that A is my cross-sectional area of the piston and P is nothing but the fluid pressure inside. So obviously whatever this force we are supplying, this force has to actually overcome the fluid pressure. So while we will be opening the valve, this fluid pressure of 600 kPa will be acting inside this cylinder also. So over here we have to supply this force that should be sufficient in order to overcome the pressure of 600 kPa. Then only it will be able to push this liquid into the pipeline. Okay, so that's why W dot, I can write that whatever this force we are subjecting, that force is nothing but equal to pressure times area. Okay, so we are writing this force as nothing but pressure times area, and that then we will be having V bar over here. Now we know from our continuity equation that volumetric flow rate V dot is nothing but equal to area into V bar. Okay, so if V bar is velocity, A is area, so my volumetric flow rate will be nothing but V dot into V bar. So in that case, my W dot will be equal to P into V dot. Okay, so now we know that volume is nothing but equal to mass into specific volume. So volumetric flow rate I can simply write as mass flow rate into specific volume. So this volumetric flow rate now I can write as nothing but P into m dot into specific volume. So now what we are having, P is nothing but the pressure which we are having over here inside this device. M dot is the mass flow rate at which liquid is entering into the pipe, and small v is nothing but the specific volume of this liquid whatever we are having inside this piston cylinder arrangement. Okay, so it means we have got some formulation that W dot is nothing but equal to P times m dot into small v. Okay, so this W work we call as nothing but our flow work. Okay, so it means while we are having certain amount of flow inside a pipeline. So obviously in case of control volume, we will be having certain pipe at the inlet, certain pipe at the outlet. So through that inlet and outlet pipe, we will be having certain amount of fluid which will be flowing in that pipe. Okay, so while the flow of fluid is happening, if fluid is flowing at the rate of m dot and P is the pressure of the fluid and small v is the specific volume of that particular fluid, so it will be requiring certain amount of flow work in order to make the flow possible. So that amount of flow work we call as, that is mathematically whatever we have seen is given by the formulation P into m dot into specific volume. Okay, so now I'll go back to my previous slide, because while we are talking about our inflowing and outflowing stream, at that point we have the flow also, because we are saying that m dot I, it means mass is flowing at rate m dot I. So that's why what I have to do over here, I have to add some flow work also, and this EI we are taking on per unit mass basis. So if I do the per unit mass for my flow work, I'll be only finding over here pressure at inlet into specific volume at inlet. Similarly, pressure at outlet into specific volume at outlet. Okay, so this particular flow work P into specific volume, which I have added over here, this appears to be actually hidden. Okay, so all other quantities from our earlier knowledge we have seen, but this was appearing to be hidden to us. So that's why what we have done actually, we have tried to see some illustration, and with the help of that actually we have tried to obtain its formulation. Now one important point I would like to highlight over here, we know from our earlier formulation what I have told you, that H is nothing but equal to U plus P into V. So what I can do, I can write over here that my EI is nothing but equal to this UI plus PI VI, I can simply write as my HI plus half VI bar square plus G into ZI. Similarly, EO I can write as nothing but HO plus half V bar O square plus G into ZO. Okay, so now one important conclusion we are making over here, that earlier I have told you, people, just to remember the formulation of enthalpy, that H is nothing but equal to U plus PV, and I told you that later on while we'll be talking about open system, at that time I'll explain you the physical significance of the enthalpy. So at the moment now you can like understand the physical significance of the enthalpy. So it is quite clear to us now that enthalpy represents nothing but our internal energy which is possessed by the fluid plus the energy associated with the flow of the fluid. Okay, because it is nothing but the sum of energy plus flowing plus flow work. Okay, so that's why we can say that the physical significance of enthalpy includes the total energy content which is carried by the flowing stream of fluid. Okay, so this is one very, very important point which you should able to understand. Okay, now let me little bit
Sir, I had a doubt that in the potential energy and the kinetic energy term, why haven't we included mass?
So what I am doing, if you see my formulation of total energy, I am writing m dot I into EI minus m dot O into EO. So we are writing this EI and EO as nothing but the specific energy. So any energy per unit mass is my specific energy. Okay, so that's why I have actually removed mass from here.
Yes, sir.
Okay, so now what I will be doing, this EI I have written in the form of enthalpy, kinetic energy and potential energy. So let me do this substitution. So what I will be doing now, this work WS plus WD, let me write as total work done by the system, WT dot, and I'll substitute over here the formulation of EI and EO. So let me go to the next slide. So if I go to next slide, my conservation of energy will become Q dot, which is supplied to the control volume, minus work done by the control volume plus m dot I into hi plus half vi bar square plus gzi minus m dot o into ho plus half v bar o square plus gzo is nothing but equal to d into ecv divided by dt. So which represents the rate of change of control volumes energy with time. Okay. So now what will be happening? This is the case when we are having actually single inlet and single outlet. Now, if we take the case of multiple inlet and outlet, so for the case of multiple inlet outlet, or we may have multiple heat and work interactions. So we may have multiple heat and work interaction also within a system. So for that case, what I can write, I can simply write sum of the energies which are there with the control volume. So that will be nothing but q dot in minus q dot out minus sum of all the work done which are transferring across the boundary of the control volume plus sum of mi into ei, okay, minus sum of me into, so here m dot I have to write m dot e o into eo, that has to be equal to nothing but d into ecv divided by dt. So that is the more generalized form of our energy equation or first law of thermodynamics for open system. Okay. Now we will try to see.
Sir, sir,
Yes,
can
please.
instead of adding that flow work in internal energy, can't we say that this is the work done on the system by outside? Like
Yes.
we are,
So what we are now talking about, we are saying that this energy is actually, this work is associated with the flowing stream. So that's why we are including that one with the total energy content of the flowing stream. Okay. Obviously, so certain system is there outside which is actually providing that amount of work in order to make the flow possible inside the pipe. But for that particular control system, for that particular control volume, we are not knowing about the exact details of the system which is actually allowing that amount of flow. So what we are considering that whatever we know at the control volume end, in that only we are including that with the entering flowing stream. Okay.
okay,
Now
sir.
another type of system which I would like to explain you over here, we define. So in case of control volume, we have now seen the conservation of mass, we have seen the conservation of energy. Now we are having one specific type of control volume, a specific type of process inside a control volume. That process or that control volume is actually known as steady state flow process. So while we are having steady state flow process, the meaning of steady state flow process is that the change in properties of the control volume with time is equal to 0. So it means that if I have certain control volume, where I have say m dot I as the inflow rate and m dot O as the outflow rate, and say I have m into cv as mass of this control volume. Okay, so if I am taking the assumption of steady state flow process, so as per the steady state condition, actually our properties of the control volume should not vary with time. Okay, so if we take this condition, in that case what will be happening, dm cv by dt will be equal to 0, because mass is also a property of the system. So that's why dm cv by dt will be equal to 0. And now if we apply the conservation of mass, we will be finding m dot I minus m dot O will be equal to 0, and in that case I'll be simply finding that m dot I is nothing but equal to m dot O. So if our inflow mass is equal to that of the outflow mass, obviously we will not be having any accumulation or loss of mass of the medium within the boundary of the control volume. So in that case, we will be finding that our rate of change of mass of the control volume will be nothing but equal to 0. Okay. So this is not the case that in case of steady state process, only our mass will be remaining constant. Apart from mass, other properties are also has also to be remain constant in order to ensure the complete steady state condition. So let me explain once again the steady state condition. So let us consider that inside a control volume, we are having some inflow, we are having some outflow, as I have just now explained you. So mi dot inflow and mo dot outflow, and within this control volume, now if I talk about temperature, it may happen that close to the inlet we are having very high temperature of say 300 degrees Celsius. At certain other location, say temperature is 250 degrees Celsius. At this particular end, say temperature is 200 degrees Celsius. Somewhere over here, you may consider say temperature is 170 degrees Celsius. Somewhere close to outlet, it may be 50 degrees Celsius. At some other locations, temperature may have a different value. For example, say 150 or say 212. So it may be any value. But the whole idea is that if we are talking about system at time t equal to 0, if at that time we are having these values of temperature at different location, if now I am going for any other time, say t equal to 5 minutes or 10 minutes, at that time also my properties value at different locations in our system should remain constant. Okay, so the idea is that we may have spatial distribution of the properties within our control volume, but at any fixed location, whatever the property value we are having, that property value actually should not change with time. So if this individual temperature at individual locations are not changing with time, obviously whatever the overall bulk temperature we will be defining for this control volume, or bulk property, any other bulk property we will specify for this control volume, that obviously will not change with time. Okay, so it is not the case that flow is not happening. Flow is happening. We are having certain amount of inflow, we are having certain amount of outflow, but after the flow has established, we are having certain situation within our control volume that properties at each and every location within the control volume actually are not changing with time. So if such assumption is valid, then we call the process to be steady state process. Okay, so now if I go for energy equation, we know that for energy, dECV divided by dt has to be equal to 0 for steady state process. So that's why Q control volume, summation of Q dot control volume minus summation of W dot control volume plus summation of M dot I into EI minus summation of M dot E into EE has to be equal to 0. So this is nothing but my energy equation for a steady state. Okay.
Sir, please explain previous slide again. I didn't understand.
So the idea of previous slide is that if we are having the inflow and outflow also happening, but within our control volume at different locations, it may have that we are having a different values of properties. Okay, but these values of property at each and every location is not changing with time. So if the variation of the property at any location within the system is not changing with the time, in that case we can say that our system is nothing but having steady state. Okay, so now one important point I would like to mention over here. So we are having actually three different conditions for the steady state. The first condition for the steady state is that boundary of control volume should be fixed with reference to coordinate system. Okay, so whatever our coordinate system we are having, actually coordinate reference frame we are having, our boundary has to be fixed. So there should not be any boundary motion. So if our boundary of the control volume is moving, then we will not be having the situation of steady state. This is first point. Second point, we are having that properties at different locations, properties at different locations should not vary with time. So that already I have told you in the previous slide. And another important point, thermodynamic state of inlet and outlet stream should not change. Thermodynamic as well as the physical state. So the state of inlet and outlet streams should not change. It means that if you are having inlet temperature say 20 degree, so at 0 time, 10 minutes time, 50 minutes time, every time this temperature, this energy content, say this pressure is there, for example, say 10 bar. So these properties, this thermodynamic state has to remain constant. Okay. If our thermodynamic state of the inlet and outlet is actually fluctuating with time, that will not be able to sustain the situation of constant property at different locations within the time. Okay, so that's why our thermodynamic state or the physical state as well as the thermodynamic state of the inlet and outlet stream should also remain constant with time. Okay, so now I'll stop at this point and we'll have further discussion in our next lecture.